Hello. Now we are going to look at the idea of installments, which are sometimes called annuities. And the idea here is that instead of making a single payment that is going to gain interest over a bunch of time, and then in the future it will have a particular value, we're going to pay in installments. So we're going to make a payment, and then in a month's time or a year's time, we make another payment, and then another payment, and another payment. And we pay the same amount in each time. And what we're interested in is, after we've made a bunch of those payments, what do all of their values add up to in the future? Because individually, each one is going to be gaining interest. So the first payment we make will have the most time to gain interest, and then the second payment will have the second most time to pay interest. So what happens when we add all of those future values together? We get the total future value of all of the payments that we've made. And we can also look at it from the other perspective of loans and pensions, but we'll start off with that idea. If we start making payments into an account, they're going to gain interest over time, but different amounts because they're in the account for different amounts of time. So if we're talking about the future value of something, so we're interested in the value of something in the future. That's what we're interested in, or that's what we know, and we need to find out about the payments. So if we're talking about something in the future, let's start off with an example that doesn't involve interest to look at the contrast. So I pay €10 into an account for 3 weeks. What's the total value in 3 weeks? Well, let's use our diagram. The first payment that we make is of €10, and it just sits in the account. It doesn't gain any interest because there's no interest in this question. So it's just going to be worth €10 in 3 weeks. And the second payment is still going to be €10 in 3 weeks. And the third payment that we make here is going to be €10. So our total value with no interest is just going to be 10 plus 10 plus 10 is going to be 30. So 10, our total value, our total future value, is just going to add up to our €30. Now, we say to ourselves, well, I'm giving the bank this money. And when I give the bank money, they're legally allowed to make money from it. They get to take it as capital and use it to make money for themselves. That's how one of the ways banks make money. So if they're going to make money off of my €10, I want to make some money off of my €10 that I'm giving them. So I'm going to make an agreement with the bank that they're going to give me 20% interest per week. Now, this is an absurdly high figure. It's just to make the numbers easy. You would never get a bank to agree to this. But for the purposes of our argument, we're going to say that we're going to gain 20% interest each week, and it's going to compound. Well, I have compounding interest now, so if I think about my first payment of €10, so I've done this conversion, and the weekly interest rate is 0.2 converted into a decimal. So what's that going to be? Well, I know that my compound interest formula is my F is equal to P on I to the T, and I know that my principal is €10 each time. I'm going to pay in the same amount each time, but it will have a different amount of time in the account. So this first payment that I make, when I make this agreement with the bank, what's its future value going to be at the end of 3 weeks? Well, it's going to be €10, and it's going to be sitting in this account at 20% interest, so 0.2, and it's going to get to sit there for 3 weeks. And what's going to happen with my second payment? Well, it's going to be €10, and it's going to get to sit in the account for 2 weeks. I can see 1, 2 weeks it gets to sit in the account. And my final payment gets to sit in the account for 1 week. So I can see all of these individual payments that I know how to do from a final value formula. To find the future value of all three of them, I just add them together. Now, in the order that I have added these up, it's just so that the powers are increasing. We'll come back to why in a moment. But all I've done is add up the last payment, the second payment, and the first payment together. And that must add up. The future values of these €10 payments add up to the total future value of all the money I put into the account. So at the end of 3 weeks, because I have this compounding interest of 20%, instead of having €30 in my account, I have €43 and 48 cents, because I got interest on my first payment that got to sit in there for 3 weeks, plus the €10 that I put in, that it sat in there for 2 weeks, plus the €10 that I put in my last payment that got to sit in it for 1 week. So I can see my total future value comes from adding up the future values of each of these €10 payments. So my total future value comes from adding up all of the future values. Well, the future value is just my compounding interest formula, principal times 1 plus I to the power of t. And what I might notice, because I wrote it in this order, is that I have a geometric series going on. What's happening between each one of these terms? I'm multiplying by 1.2. I'm specifically multiplying by 1 plus the interest rate, written as a decimal. So this is a geometric series that has a first term of 10 times 1.2, or €12 in this case, and then my common ratio, or I can see I'm multiplying by 1.2 each time. That's what gets me between the terms in my series. So for larger questions where writing out each one of these terms individually would get annoying, we can use the geometric series formula. And again, the argument we're using is this is a geometric series because our geometric ratio is constant. So I'll write that out. So the most important point here is I have my geometric series because if I take t1 divided by t2 or t3 divided by t2 for my geometric series, that must be a constant. And I can see that if I divide that stuff out, 10 divided by 10 and 1.2 squared divided by 1.2, I'm left with the same number each time. 1.2 cubed divided by 1.2 squared would leave me with 1.2 as well. So I've got a geometric series. And therefore I can use a geometric series formula to simplify all of this, adding up my future terms. So that's how we can think about this in terms of putting money in and getting the future value of it. But sometimes we're interested in loans or pensions where we're interested in the present value of a loan or the present value of a pension. So a loan is where you get a bunch of money and then you have to pay it back in installments. We don't tend to get a loan for like €100,000 and then in a few years' time we give the bank €100,000. We tend to pay that money back in installments. But this time we need to think about the way that the interest is going to work. So if we take our example here, or sorry, let's start off with how our present values would work. We know that the final value is equal to the present value times our interest business. Well, if I rearrange that formula, if we take our formula here and we divide by the stuff that is multiplied by p, so that we isolate p, the present value, if we're interested in the present value of future payments, like we are for our loans, divide both sides by that, and the present value is equal to our future values, our repayments. That's going to be the same amount of money each time, but they're going to be discounted by a particular amount that we can see comes from our compound interest formula. So let's take this example. How much of a loan can I afford if I pay back €20 a month for 3 months? Well, again, let's take the situation where there's no interest. The first payment I make is at the end of the first month. So I get whatever amount of money I can afford to get a loan for or here, but I'm going to start making a payment back of €20 after the first month. And the second time, after the second month, I'm going to make a payment back of €20. But it's still worth €20 because there's no interest involved in this question. And after 3 months, I make my final payment, and it's still worth €20. Well, what's the present value of all of those payments? Well, I just add up those €20. So I should be able to get a loan of €60. But the bank says, hey, we're giving you this bunch of money now and you're not paying us for a while. So we're not going to accept that this €20 that you're going to give us in a month's time is worth €20 to us now. We're going to charge you an interest rate of €30 per month. So your value of your money is going to go down by this €30, or by this 30%, I should say. So what's going to happen when I start to pay back my first piece? Well, to my first payment of €20. Well, I know that the present value of that payment is going to be my €20, the amount I'm paying back, divided by this interest business. So it's going to get discounted by my 0.3 over the month. So instead of the bank saying this €20 that I'm paying you is worth €20 to us in the present, they're saying I'm discounting it by this much. This interest rate means that I am going to value the €20 you give me in the future less than the €20 or the €60 that I might be giving you now. So to work out the present value of the loan that I could afford, I have to take into account that the bank is valuing this future €20 less than €20 right now. That's what the interest rate means in this case. So what does that mean for the next payment? Well, that's 2 months in the future. So the bank is even less impressed with that. It's going to say, I'm going to discount the value of that by 2 periods. And the third payment is all the way 3 months in the future. So that €20 that you're going to pay them in 3 months is worth even less to them now. They're going to value it even less. The longer they have to wait to get this money, the less they value it in the present. And you can probably empathize with this. If I said I was going to give you €10 in 30 years' time, it's a lot less interesting to you than if I say I'm going to give you €10 right now. So we have our payments and they are being discounted by, they are less valued by our interest rate. So how do we get the total value of the loan that we could afford now according to this interest rate? Well, we add up the present value of all of these future payments. So my first payment that gets discounted by a 1 month's interest is only going to be valued at €15.38. So the €20 I give in 1 month's time is the bank is saying I'm only going to value that at €15.38 because it's less valuable to me to get this payment in the future. And after 2 months, that €20 is only going to be worth €11.83 to me in the present. And after 3 months, it's only worth the €20 is only worth, or 3 months into the future, that €20 is only going to be valued at €9.10 in the present. So right now, the money would be €20, but in the future, it's being valued as less valuable to the bank. Now, you do an equivalent thing when you are taking out a pension. So with a pension, you need to have a big block of money, and that's going to pay for you getting paid effectively a salary from that lump sum of money. But as you go further out into the future, say you were going to get €20 a week for a particular number of weeks, the €20 a week that you get for your first payment of your pension is more valuable than the €20 a week you're going to get in 30 years' time. So we do this as well with pensions. So anytime we're interested in the present value of a bunch of future payments, then we're going to look at the question in this way, where we end up dividing by powers of R1 plus R interest rate. But again, we might notice we have what's changing between each of the terms in our pattern here. Well, we seem to be dividing by another power of 1.3. So again, we end up with a geometric series, and we're going to write down our terms for that. So for larger sums, we can see that the geometric ratio ends up being 1 all over 1.3 when we do out our... Do I have that written right? Yes. We end up with a common ratio. We'd end up with 1 all over 1.3 each time. So for larger questions, we can use our geometric series formula. So that is what we need for now.